how's it going? Welcome.
Hey, thanks for having me, Dion.
Of course.
It's a pleasure being here.
Where are you coming from, actually?
Yeah, I'm dialing in from Egypt, Cairo.
Oh, nice. Well, thanks so much. That's a little bit later than here, even. So, thanks for
A little
staying
bit,
up
yeah.
late for this. Uh,
Yeah,
and
thanks. I'm really excited.
yeah, awesome. Well, I'm gonna get off the stage myself and hand it over for you and get your slides up, and then we can get going and go from there. So, have a great chat.
Great, thanks, Dion. So, reliable DevOps agents for self-driving infrastructure. So, let me tell you a bit about myself. So, I was a founding engineer at a couple of other startups, always building infrastructure and doing like the security work. Um, so, I've been writing code for 10 years now. I really like doing calisthenics, like body weight exercises, riding cruisers, and like volunteering, teaching people like how to code and how to do infrastructure. I really like developer experience and security, which are usually two things that never mix well. But yeah, that's what I'm mostly interested in. So let me tell you a bit first about the problem. Like, why is this necessary? Like, why do we need the self-driving infrastructure in the first place? So today we've been interviewing engineers, like developers, software engineers, and engineering leaders, like hundreds of them every year since we started Stackpack. Because, like, as you guessed it, like we're working on trying to make infrastructure self-driving with like reliable configurations and agents, which are things like that don't mix like security and developer experience. So like agents and reliability. Like, how do you explain it? So here, like, I grouped a lot of the feedback we got from different people into like fictitious three personas. So DevOps engineers see that developers have no clue what they're doing. So they don't know a lot of things about the system internals of all the DevOps tools, of all the complex infrastructure they deploy their apps on. At the same time, platform engineers are sick of spending the majority of their time on support tickets instead of doing platform work that optimizes costs or like makes the developer's life much easier. On the other side, developers, like, they see a huge mismatch or like misalignment in priorities. So developers want to get this bucket or like get this feature out. They want this to work, while DevOps or like the infrastructure or platform team want to move to Kubernetes. So like there's a lot of misaligned like priorities and a lot of like bottlenecks in the infrastructure. And this pain keeps growing even with internal developer platforms and the abstractions people are building to make this thing easier. And the reason this is so tough is because there are like hundreds of DSLs, like a different configuration parameters and languages and schemas that you need to learn to figure this out. So we call this DSL hell, like domain specific language hell. It's not just the DSLs, but also the schemas themselves configuring. So like YAML is sort of like a data language or DSL, but then there's like hundreds of ways of writing YAML to configure all these tools. So you're not just writing a programming language and building stuff, but you're configuring other tools, and these tools have internal top secret information about how they operate, and you need to be aware of that to be able to write these tools. So it's like a very minority, like the minority of developers understand these tools really well and understand all the different combinations. And I've rarely seen a DevOps engineer or infrastructure person understands all of them, but like always a subset. So that's one reason why this is very difficult. There are a lot of things to learn and you have to keep in your mind to be able to do this kind of work. Another thing is that most of the abstractions in this, like we have layers of abstractions in infrastructure, and almost all of them are leaky. So for example, if you're trying to create a pod on Kubernetes and set a limit, so limit is a contract with the resources you allocate to a specific workload you're running. And then you would see, like, you expect, or like most developers expect, that this limit would be honored by the platform. But then what happens, they find their pod or workload killed because it's ran out of memory. And they can correlate that this has to do with the limits. So like the underlying layer that operates the workload just kills it if it exceeds the limit. So this is leak abstraction. So developers have to keep in mind how this thing works internally, how like the kubelet like runs the container or like there's workload, and how it deals with the memory limits. The same thing goes with corner cases for Dockerization. Like cloud-native buildbacks are amazing, and people build internal Docker files in a reusable way so people can keep building the same apps over and over again, but they rarely work because of all the corner cases. Same thing with something like Terraform. You have the underlying layer that communicates with infrastructure. Like Google Cloud just made an abrupt API change that just broke a lot of Terraform code that deals with Google. So these are some of the difficulties we see, but also people keep talking about it. So in real life experience, like people keep complaining about LLMs are decent at writing code, but they suck at infrastructure, which is like the worst part of coding, set up an infrastructure. And this guy here, like after posting this, after a month later, he just like decided to throw in the towel and say, okay, AGI is here once an agent can configure a Docker container, set up CI, and deploy my app. That's how frustrating it is. But like these are all opinions and like subjective opinions of why LLMs and like are suck at this kind of work. But like there's a paper about one of the reasons they are terrible at this work, and it's because they suck at domain-specific languages and configurations in general. So from this paper, you can see like a trend here where LLMs are really good at very popular languages that change not very frequently over the years, versus other languages like the long tail of DSLs and the long tail of non-popular languages anymore. They're not that good at it. At the same time, when you see like the stack eval versus stack unseen, the two data sets in this like paper, which compares like asking about fresh knowledge versus old knowledge, the LLMs were already trained on, they perform really bad like on fresh knowledge. And this is the mix we get in DevOps tasks. So if we're trying to compare coding tasks and DevOps tasks on like some factors based on like everything we discussed so far, you would see that the feedback loop for coding tasks is super tight. So you get like when you have a coding agent and there's a human in the loop and it changes something, you see it, you can validate the code and then keep iterating quicker. But for DevOps tasks, it's usually much longer. So you're trying to create a virtual machine or a database on AWS, and you have to wait for 50 minutes at least for it to be ready. So then you would know if you created it with the right parameters, for example. So like this is a dumb example, but like you get the idea. The feedback loop is super slow. Another thing that's different between regular coding tasks and DevOps tasks is like the user knowledge. So users or coders or developers using these coding assistants, they have high knowledge of the task at hand, which is writing code. But less than 3% of developers are expert at this kind of infrastructure work. At least less than 3% do this full time. Also, the syntax for coding tasks is super popular compared to many domain-specific languages. And the frequency of this changes. Like the coding languages change rarely, or like the syntax and the features, unlike other DevOps tool configurations, because the tools keep changing quickly. They add features, and these configuration languages configure the tools. So the more tools, the more complexity, the harder it is. And final thing is about the context itself. So most of the context you find for coding tasks is local. So it's like you're developing locally in your machine. So everything you need, or almost everything you need, can be run locally or mocked locally. But for DevOps tasks, it's super hard because the context is mostly remote, like a bucket or configurations through the AWS API, or like Kubernetes clusters deployed in production with a specific set of parameters or workloads that are not available locally. So this is the reason why LLM agents or like coding agents are really good at coding, but they suck at infrastructure or DevOps work. So what usually happens is they like run out of steam, like keep going around in loops, or they're unable to accomplish these tasks. And like this is our analysis of like at least what we learned over the past couple of years. So self-driving infrastructure. A lot of people see it this way, like Cybermen from Doctor Who. Like they're going to take over humanity, basically like push humans out and be more efficient, be more like stronger when it comes to doing these kind of infrastructure tasks. But like from my experience, we're developing agents and how we see them operate. We think self-driving infrastructure is going to be something like this, with a lot of minions that are stochastic agents. They sometimes spit out gibberish and they do funny things, like they keep walking around. But like when effectively managed and guided, they can accomplish great things. Like they get the job done really well with human guidance, but they're a force like to be reckoned with. So in here, like today, we're going to talk about like how we're working on this. First, I'm trying to help you imagine what a self-driving infrastructure would look like with these kind of minions. But when you're thinking about agents that operate infrastructure, like I want you to picture minions, not Cybermen. So what would self-driving infrastructure look like? So theoretically, a self-driving infrastructure would have these capabilities at least. So the first thing is you would have agents that work 24/7. So these agents can do maintenance tasks in the background. They can handle support tickets. They can tune your system live 24/7 without having people on call. And they'll be able to keep doing that over and over again. Second thing is this self-driving infrastructure will be technology agnostic. As we mentioned earlier, like having a lot of tools and a lot of cloud providers with different semantics and different ways of describing things make things super difficult. So having these self-driving infrastructure capabilities, it shouldn't like this self-driving infrastructure shouldn't care about like the tools it's using or the cloud provider. It should operate across them and like orchestrate across different cloud providers and technologies easily. The third thing is you have a dynamic platform UI. So as you can see with vibe coding, like you can build simple applications and interfaces really quickly or prototype more complex stuff really quickly. And the same thing would be happening in a self-driving infrastructure within your internal tools. So your internal tools would keep evolving, they would keep changing depending on the use cases, which fixes a huge problem we have with like internal developer platforms today, which is like static abstractions. And these abstractions, like they have to keep evolving. But instead of having a product manager and a developer that like put a lot of effort into maintaining this and keep changing them, because they can change it at the same rate that developers would expect the platform capabilities to evolve. So this can be done automatically, autonomously. And finally, two major, very important things we haven't tapped. So like we have super complicated infrastructure service with a lot of great capabilities, but we still don't have that much like intelligence in cost optimization and scaling. So what this would entail, like imagine the scenario, like you're running a workload in a Kubernetes cluster, but then the self-driving infrastructure would detect that this workload is like, while monitoring the data, is more suited for something serverless. So it would move it from your EKS cluster to Lambda for a specific duration with zero downtime, because this is the most appropriate kind of like compute platform to run your workload on. So this would help you reduce costs dramatically and help you with scaling depending on this. So you wouldn't care anymore about like the underlying compute, because your infrastructure is going to be able to migrate itself, like move these workloads around to save costs and optimize scaling whenever you have to deal with it. So things like scaling to Lambda and then going back to Kubernetes or scaling to zero would be easy, and it wouldn't care about the underlying compute platform specifications, because these things can be self-driving. So let me give you some examples of how this would look in practice with a couple of use cases from different personas. So having these agents run 24/7, you can do things like routine maintenance, and not the trivial kind of routine maintenance, something like this. So if you've ever had to upgrade Kubernetes after like months, like you get a new Kubernetes version every 3 months, but like imagine you spend a year or two like not upgrading these Kubernetes clusters, and then you have to do it all at once. So you would prompt this self-driving infrastructure to upgrade my EKS cluster to the latest Kubernetes version available. And then it would come up with a plan on how to do this sequentially, because you cannot do it at the same time. And if you're using infrastructure as code like Terraform and you're trying to do that, it would fail. Like it's not able to do this kind of incremental upgrades autonomously. So the agent will be able to do that. So the self-driving infrastructure will take this instruction, go to the cluster, read the documentation, the changelog between the different versions, migrate your workloads, test it, make sure everything's great, upgrade the like API server, keep doing that until you reach the latest version. And this will be able to this will be done, can be done overnight. So you don't have to monitor it, you don't have to like keep guiding it on how to fix these issues. It will be able to figure it out. And this is what agents are great at, like figuring out like new unpaved roads to like accomplish a specific goal. So this is one thing. Another thing would be intelligent abstractions. So this is like something really painful. It's like, so different cloud providers have different ways of like naming a firewall. And so the firewall is some sort of like became a high level user intent. So if I'm a security engineer and I faced this before, like, and I'm trying to figure out, okay, where are like the firewall rules where all inbound traffic is like allowed within the cluster or like within my environment? And I'll just ask it this, and it will be able to figure out, like translate the high level intent into lower level executable operation and figure out, okay, a firewall in an AWS, like in AWS is called a security group. At DigitalOcean, it's called a firewall. And on like Google Compute, it's called, or Google Cloud, it's called a firewall. So we'll be able to figure this out and aggregate the results across different clouds, like in a hybrid environment, and show them to me without having to break this down and without having to define a rigid abstraction. So this is what I meant of like having more intelligent abstractions. Another kind of example is keep trying while we sleep. So if you're trying to, remember when I mentioned like creating Docker templates, Docker file templates, or using cloud native build packs don't work in every single environment, in every single case, because applications are not identical. So this is a great application for self-driving infrastructure. It will be able to containerize an app, work on iterating, coming up with a plan, creating progress checklist, keep iterating on containerizing the file, but like not just spitting out a Docker file, but actually building the image, running it, and testing the health check to make sure it passes, and figuring out issues along the way. So you can see from this screenshot, my self-driving infrastructure is able to generate a compose file to test the Docker file that's running properly, spins up a database locally, configures all the variables, all the secrets to make sure the app is working fine before spitting out the final Docker file. So it's not just like trivially generating configurations, but actually validating that these configurations work. And a self-driving infrastructure wouldn't be complete with live deploy. So you can already try any of the existing like coding agents to do vibe deploys on different environments. But the cool thing here is these are context specific. So you're able to vibe deploy on your own custom infrastructure on your cloud account, and it will follow security best practices. So this is the tough part, like not just vibe deploying anywhere, but vibe deploying in your own environment with security best practices. So here I'm asking a self-driving infrastructure agent to deploy an app on my AWS account with TLS configured and to configure a specific domain to point to it. And it goes through this and figures out everything. And if you can see, like, it's pretty tiny, but like when it's configuring the database here, it didn't like create a plain text like password and spit it plain text into like the terminal, but created it in a file and use this file to add the password to the API without having to export this in a shell. And it created a secure password, like a long enough password. So it configured TLS and added a systemd file to restart on server restarts. And this is like, there's a lot of details involved in like vibe deploying or like VibeOps, as Ray Myers called it. So there's a lot of details, and getting these properly within your environment is hard. I mean, even developers struggle with this today because they don't have all the details and all the things they should do right at the same time in their brains when they're trying to do this. So it's super tough. So the cool thing about these examples, this is already possible today. So this is not the future. Self-driving infrastructure agents or DevOps agents are able to do this today, but is it reliable enough? Which is the biggest question. So like if you're going to try having a self-driving infrastructure with these capabilities, like how reliable are agents today? And how can you make them better? Like how can you be sure that you can sleep at night while the agent is self-upgrading your Kubernetes cluster with zero downtime? Because this is a very tough thing to do. So to talk more about like how we think about reliability and what we've learned so far, making these agents reliable in a very critical task like building a self-driving infrastructure, let me share with you how we think of an agent. So welcome, Norbert. So this is one of the minions we've been building or experimenting with, and it's just the simplest possible agent. So Norbert, as you can see, like the naked minion, it thinks, and then it takes one of two actions. So just like very simple actions, and that's the first thing an agent can do. Like an agent can autonomously decide which action to take. So it can be two actions, which is the minimum, so it has some choice, or it can be many actions. The second thing is after it takes an action, it affects the external world. So it has some way of modeling the external world or observing the effects of its actions. So it can iterate, which is the second thing of making an agent. So the agent can take actions autonomously, choose which actions, and it iterates, keeps taking actions to accomplish a specific goal. And that's the third component. An agent should have an end goal or somehow a measurable end goal to be able to evaluate its reliability. Otherwise, it's super hard to say if the agent is done, and it's super hard to say if the agent accomplished its task successfully. So this is not as easy for every single domain. So in our domain, we're fortunate enough is like if you're trying to containerize an app or like deploy something or debug something, you can find in a deterministic way, like validate that the agent accomplished its goal. But like things like documentation generation is much harder, for example, or writing is much harder. So in this case, having an end goal in these agents makes it easier to evaluate their reliability and make them better, or like at least be able to observe this to see how we can improve it. So getting this out of the way, how we define agents, agent takes actions, it iterates until it reaches a specific end goal. So how we think about reliability, we split agents into two parts. You see there's the think part, which is the first thing we're trying to make it reliable. So how it thinks, how it comes up with tools or like actions to take. And the other part are the actions themselves, because you can have as many actions as you want. And we found out that the actions, like the performance of the actions themselves, affect the agent dramatically. So like the impact of having action, like the choice of actions and how intelligent these actions are, like how, for example, like you can have a very simple action that does a lot of things, or like specific actions dedicated to stuff. And there's a trade-off, because the more tools you add, the harder it is for the agent to come up with the right combination of tools to execute. Sim to a human being, like if you give a human being too many options, like their brains will just overload and like you get decision fatigue. So the same thing happens to agents. So we're splitting it between reliable thinking and reliable actions or reliable tools. Let's start with the reliable thinking. So when we're talking about reliable thinking of the agent, is how it comes up like after observing the external environment, or like the distilled version of the external environment in its memory. Like what actions would it take and in which order? So reliable thinking is more focused on the brain. And when you're thinking on the brain, we came up of like in the literature, you would see 3 ways of evaluating success. So you can check the end goal, which is the easier, the most straightforward way, because if the agent doesn't accomplish the end task, like it's failed. Like it couldn't build an app runs, or like couldn't migrate your Kubernetes cluster, or couldn't deploy stuff on ECS, or couldn't containerize an app. So it's relatively easier to reason about the end goal because this is the task we're trying to accomplish. But then some people use sub goals because sometimes the end goal keep failing and you're not sure why. So if you divide things into sub goals, you get a better idea of why the end goal is not accomplished. So this is another way to measure success. And finally, the most complicated way to measure success is the action trajectory. So the agent takes specific sequence of actions given a specific input. So a snapshot of the real world, or like the snapshot of its memory or state. And then it takes specific actions based on this like kind of snapshot. And then you evaluate this, like, is this the right course of action given the initial starting parameters, which can be fixed. So this is another way to measure like the evaluating success. So at StackPack, we're still having gone through like all three. We've been doing a lot of work with end goals and sub goals, but we still haven't started evaluating trajectories yet. But it's something on the roadmap, something we want to dig deeper in, because there are a lot of common subtasks that are very common between different kinds of infrastructure or DevOps tasks. So it'd be great to see like how trajectory of agents perform on these specific like sub goals or like sub trajectories. So since now we can like evaluate like the success criteria, we know when the agent is successful. We have to pick specific metrics because we're trying to evaluate how reliable the thinking process is. So some of the metrics people use that are generic enough and you can apply to different domains, like these kind of like the evaluation criteria. You can also apply this to different domains, not like DevOps or infrastructure specific, is pass at K, which means if you give the agent K attempts, what's the likelihood that's going to succeed at least once? So K at 1 is the likelihood that this agent is going to succeed like on a single try. At K at 4 is the likelihood that this agent is going to succeed at least once given 4 attempts. So this is a very good indicator of can the agent actually accomplish what it was designed to do or not? So this basically asks that, like, is the agent capable of doing this or not? But it doesn't measure reliability, because if the agent is capable of doing something, every one in like 10 trials, doesn't mean like every single user or every single time we're going to do this, it's going to pass. And this is very difficult for very security, like very critical infrastructure tasks. So there is also pass power K or pass at K, which means like given K attempts, what is the likelihood that the agent would pass K times? So assuming like pass to the power of K is pass to the power of 4. So given 4 attempts, what's the likelihood that the agent is going to pass 4 times, which measures more reliability, and it's a tougher metric to hit. Another thing we measure is the number of steps, because we notice that the more steps the agent does, the more it tends to hallucinate and the longer it takes it to accomplish the task. So if there's something critical I want to recover, for example, from a failed deployment or rollback, or fix something that you can do reliably with a deterministic system and you need an agent, the agent finishing its job quickly is a great thing, like it's the desirable thing. At the same time, if you're not doing a lot of state or context compression and you want to keep steps, the more steps you add, the larger the context blows up, and the more likely the agent will hallucinate and lose track of what it's trying to do. So it's like dangling a banana in front of a minion. So the minion, when it sees the banana, it will just abandon the task and chase the banana because it's just overwhelmed and it sees something interesting and just chases it. So the agents that do a lot of steps and keep a lot of steps in their memory, they tend to lose track of what we're trying to do in the first place. And the same thing happens to me sometimes, but that's why we measure the number of steps. So the final thing is the cost of success, which like how much would it cost us for a containerization agent to be able to Dockerize an app successfully? Because as you see, like it can take on a containerization process and take 15 minutes. And I can, like, if the success rate is 50%, I could just like run it 10 times overnight until it's successful, which is fine. But how much would it cost me? Like, because what if it costs me $2,000 or like $10,000 to containerize an app? Then it doesn't make sense anymore. So part of the problems being solved is the cost of the problem itself. Like, would it cost more than it would save us to do this kind of task? Like, if you have a big migration project that would span 3 years modernizing your infrastructure, and like this thing is going, like the self-driving infra or like DevOps agents is going to cut this down into 80 months, like would the cost of doing so be, like, given the time and everything, like would it be worth it or not? So this is an example table of one of the very first evaluations we built. So the task here was being able to deploy and like a full stack application on AWS, a stateful application on AWS with like all the bells and whistles and with all the security best practices, including TLS, secure passwords, private database, button-up security groups, stuff like that. So here we try different applications with different technology stacks, trying to make it as diverse as possible. And we measured pass at 1 and measured pass at 4. And you can see here, like we also added some custom metrics, which is something you might do, like adding custom metrics specific here. So here we wanted developers to see how fast it is to deploy these apps. So we added in the mix like a deployment time. So depending on the evaluation, the kind of metrics and success criteria I shared are very generic, but you can also add in the mix like very specific things. So once we got this, we found out like two major takeaways. The first one is sometimes the success rate is really high and it's really fast, and it doesn't mean like, okay, so this kind of task, like it's really good at it, so it's very reliable, it's almost as if it's deterministic. So this is great, so this agent is great, like we didn't need to optimize further for this kind of like specific task. But in other tasks, we found out that the pass at 1 is very low, but the pass at 4 is much higher. Like as you see here, like if I give it 4 attempts, it would go up from 50% to just like 93%, which is very high. Like you can afford to do this in every task. Like some tasks like Dockerization, like it's not very critical. You can leave it doing that overnight, try over and over again. And every trial is just an hour, which is amazing. Like it would take me 4 hours to deploy this kind of app. But here we can afford it, but not all applications we can afford this. So pass at 4 can be tricky, like pass at K can be tricky in very critical situations. And then you need to do the pass power K to make sure it's consistent and reliable, because you don't want to rely on an agent in something critical and then you find out like it's just like hallucinated or like broken infrastructure or something. So not always like pass at K can be like misleading in some cases, but yeah, you get it. So the big elephant in the room, especially for infrastructure and DevOps tasks, like there's no available public data sets, or like there are very few data sets, and with a lot of stale data out there. So how do we evaluate without data points? Like how we gather these data points? So the first thing we started is like aggregating open source code on GitHub for infrastructure. But unfortunately for our domain, like most of the code is super old and it's outdated and it's not like as high quality as you would see. And it doesn't represent the actual fact, because like infrastructure configurations, people don't usually put that on GitHub. Like they keep it in private repositories for their infrastructure, and they're like it's a closely guarded kind of code for any organization. So this is terrible. Like we weren't able to rely on this much, but it gives us a hint. And then we do synthetic data. Like we generate a lot of synthetic data, like running the agents, generating code, and using these to build evals. And they're surprisingly really good, because for very complex tasks, even a human like doesn't have like 100% success rate. So synthetic data, if like the success rate is like 70%, this would exactly be the success rate if you give a human the same time to write a data set. But the highest quality of data you can get is from real customer support cases. So we take these cases, we study them, and then we anonymize it, like go back to generate synthetic data based on these cases, like guided synthetic data. And these are the high quality you can get. And we always start seeding these data evaluation data sets with handcrafted data. So like we create use cases manually to try spread it, like to handle corner cases and stuff like that, which is like the highest quality data we can get. But we're going to get a lot of quantity, like a higher quantity of this kind of data. So something else we do, like this is for the evaluation, but what should you do after production? So we use a lot of, we tried a lot of LLM observability tools. They're all pretty much the same. We use LangFuse at the moment. So LangFuse, like it gives you like kind of sort of traces for like the LLM workflow. So if you have complex workflows or agent, you can track everything, like all the prompts, all the sequence, the input and the output, and so on. And then you can see when something goes wrong. You would extract samples from this like production observability data and then add it as a handcrafted data point to your evaluation data. So this is very important, not just to understand what's going on in production, but to also be able to refine the evaluation data and keep like building this flywheel, making these agents better and better and more reliable. So this is the first part, reliable thinking, or like how to make the agent thinking process better. Another part is reliable tools, because we're huge advocates of the approach that like we're trying to have very few but super high quality tools, and we found out that these make the agents much smarter compared to very dumb tools. So instead of the agent taking like 20 steps to reach a specific conclusion or like do something, they can just do a single step, which keeps like the context from blowing up, and it keeps the agents much simpler by like offloading or like delegating these tasks to a more capable workflow or a tool. So here I'm going to show you a couple of examples of how we're evaluating tools, because evaluating tools is trickier than agents, because so it's sort of like it's easier to get like to build an eval data for this, like for tools, but it's harder to come up with like success metrics, because they vary greatly. Like every single tool has its own success criteria and metrics to measure it with. So for the context retrieval evaluation, like here we're trying to retrieve specific parts of your infrastructure that are relevant to a question or to do precise like surgical edits to accomplish a specific task. And here you can see like we use a recall because we are optimizing for the amount of information you retrieve for the context in your machine, like in your environment. In another case for code generation, for example, and Terraform specifically, we can't just like validate the quality of the code. We want to make sure this code is applicable in production. So we have a metric that measures zero-shot Terraform planning success rate. So we take the code, we actually try apply it in a sandbox environment and see if it succeeds, and then or like at least plan it against this environment and see if it succeeds. And this is like a high enough bar, I think, so far, at least so far, for Terraform code generation. And this is basically how we evaluated this tool call. So as you can see, like tool calls have like you have to be creative on how you evaluate every single tool call because like and how important this specific task is. So you can distribute your like weight or like amount of work evenly, so you can like deal with the lowest hanging fruit first, but then like add specific like harder requirements and harder as you're accomplishing more scores. So the more higher scores we reach on specific like metrics we're evaluating tools at, the harder we're trying to make the metric or the goal, so we can keep them getting better and more reliable. So that's it. But as you guessed so far from this Cyberman, I'm a huge fan of science fiction, and I found this quote very relevant from like one of the very famous like books written so far on robotics and AI by Isaac Asimov, and it says like there was a time when humanity faced the universe alone and without a friend, but now they have creatures to help them. And these little like minion kind of agent guys, they're super helpful and super funny, especially when it comes to some like very dull and a very like painful kind of work developers have to deal with infrastructure. So this is a great chance to try control these creatures and like make them better, so we can sleep better at night and like we can enjoy coding again. Thank you so much. So please reach out if you're interested in discussing this more. I would love to show you what we're doing and talk about these kind of like agent evals because they're super tough and they're super interesting. So yeah, this is my LinkedIn. Thank you.
Thank you so much, George. That was awesome. Yeah, that was really fun. It resonated a lot. And right at the end there with the Asimov quote, like I recently had a project where I had to hack on something for a couple weeks, and it was just me and some bots. And it felt different than back in the old days, where like I feel like I've got like a bit of a thought partner, and I like write up like mini specs and send it off to my minions in that case to do work. And it was a very different experience than kind of doing it solitary. I do like working with humans, so I like having both. I don't just want to be locked away in the basement, but yeah, it's really fun. So on. Before you go, I got a couple questions here. So this is one. Have you considered using reinforcement learning techniques to guide these agents and potentially improve their success rate compared to relying on rules and like? Any thoughts there?
Yes, definitely. Yeah, definitely. Like one of the major challenges with agents is picking like at least evaluating like or improving the thinking part. Like we talked only about evaluation, like not techniques to improve the performance, but like one of the major things with thinking is choosing the right tool at the right time. And this is where like reinforcement learning policies are super important. Like you can optimize the tool choice based on like successful runs, but like the trick here is figuring out like how to create a reward function that optimizes for like the success rate. Like what do you incorporate? Like there are some papers that incorporate a mix of have like taking the end goal and the process at the same time, and like add a mix of like a weighted sum for like accomplishing sub goals and end goals, for example, in the reward policy. But also you need a lot of good data points to be able to train this. Yeah, so this is definitely something we're considering and working on.
Yeah, I kind of picture like having minions in these isolated worlds to be able to try things out and be able to kind of learn over time and do the Alpha Zero thing, but in the world of DevOps. That's really fun.
Yeah, but it's super slow. Like we have cloud sandboxes and we let these agents, like we have a minion farm where these agents are run freely, but like it takes sometimes like 15 or like up to 60 minutes to accomplish a specific task, which is super slow to generate enough data, enough realistic data.
Oh man, that's fun. So if I'm newer to this world, like how do I build the trust to the point that I can actually sleep at night and allow this system to go off and be, self-healing and doing things, and not having me, having my mind wake myself up at 2 a.m. worrying about, what happened. How do you kind of go through and build that trust?
So we have two things at the moment. We're still discovering, like we're still exploring this, but like one of the things we found out that really helped and is like showing the users or like the developers the thought process of how it comes up to these conclusions and how it's thinking about accomplishing this. So the more you add tracing data, like how you, for example, like how we're debugging the systems, the more we show users these kind of like internal workings, how these things are built, how they're evaluated, how they think, the more trust they evolve. And like it sets expectations right to the right time. So like the more you see them considering a lot of angles you never considered before, like storing secrets in encrypted files and not like in plain text and stuff like that, the more you realize, okay, these things are actually more reliable than I thought, and then you would trust them more. So this is one thing. Another thing we're doing is we're starting like opening up like these benchmark results. So the first time we launched an agent last year, we published with it like a big table with what it's good at and what it sucks at. As you can see, like we added a row of like, okay, this cannot deploy Supabase. Like the success rate is 0 even after multiple trials. So we show developers that we think like which scenarios these are optimized for and which scenarios we're evaluating for and which other scenarios are still not very explored. And you can trust them to do these kind of things well.
Got it. Nice. And then if I'm a developer that hasn't done the DevOps thing yet, do you feel like the world of AI makes this like more approachable? Like, would you like recommend that they actually start getting into DevOps now, and that the water's warm?
Yes, definitely. I mean, like a lot of developers I meet are scared of doing infrastructure work because they don't want to mess something up. Like they don't want to leave a firewall rule open or like leave a database public and so on. And you would see like it's much easier to align like the like these kind of agents or like these kind of chatbots or like the code generation, whatever you're doing, with specific security policies. So like the defaults are really more secure than what an average developer would do, because because developers are scared of touching this kind of work. But I think now it's more manageable. At least you can think, like you can check the thought process of these agents and you can do it yourself. But like it's very educational. Like I've learned new AWS CLI commands by watching these agents work. I didn't know, for example, there's a subcommand for you to wait on a specific resource to be ready. Like I always wrote a bash script or like use something else.
That's fun. Awesome. Well, George, thank you so much for taking the time and staying up late to show us all of this stuff. We really appreciate it, and look forward to chatting on Discord and the like and continuing the conversation.
Amazing. It's my pleasure. Happy to be here. Thanks for having me.
Yeah. Cheers.